Good morning to all of you. Today we are starting our syllabus with chapter 1 nuclear reactions. As we know, the nuclear reactions first topic is Bethes notation. In Bethes notation, a nuclear reaction is generally represented by the equation indicating the nuclear characteristics of the reactants and resultants as. So this is the nuclear reactions represented where in this nuclear reaction, X stands for target nucleus. This A stands for projectile affecting the reaction. B for the particle ejected, or it is also known as ejectile. And Y is the product of the nucleus or recoil nucleus. So here in this nuclear reaction, X is the target nuclei, A is the projectile, B is ejectile, and Y is product nucleus. Here, the nuclear charge conservation is observed. That is, the nuclear charge on the left hand side of the nuclear reaction must be equal to the sum of the nuclear charge on the right hand side of the nucleus. That is, Z1 plus Z2 is equal to Z3 plus Z4. So this is the nuclear reaction generally represented, and here X is the target, A is the projectile, B is ejectile, and Y is the product. Z1, Z2, Z3 are the atomic numbers or charges. A1, A2, A3, A4 are the mass numbers of respective uh, nuclei. This nuclear reaction, according to the Bethes notation, is represented in a short form in this way. That above nuclear reaction is represented according to Bethes notation by this equation in short form, that X is the again target, this is the projectile which is bombarding on the target to form the nuclear reaction. B is the projectile B is the ejectile which is ejected from this nuclear reaction, and Y is the product. So according to Bethes notation, the reaction is represented in this way. The target nuclide is written first, this is the target nuclei, and the product is the last, this is the product nuclei, with projectile and ejectile particles inside the parenthesis. So inside the bracket we have to write the projectile and ejectile. So this is the these are the four examples of writing the nuclear reaction in the form of Bethes notation. So here the magnesium 24 is the target nuclei. This D is for deuterium, is the projectile which bombards on this target and form the product nuclei sodium 24 with the ejection of this alpha particle. So in this case, you can see that we need to conserve the nuclear charge. So we know the magnesium has atomic number 12, sodium has atomic number 11, and deuterium atomic number 1. It's an isotope of hydrogen, and alpha is the helium particle, we know that, and its atomic number is 2. So here 12 plus 1 is 13, and here 2 plus 11 is 13. So from the left hand side and right hand side, the nuclear charge conservation must be there in writing this nuclear reaction in the form of Bethes notation. Second example is again chlorine 35 reacts or bombarded by the neutron. With the ejection of proton, it forms the sulfur 35. Third example is again for sodium 23. Here the projectile is neutron, ejectile is gamma particle, and this is the product sodium 24. Similarly here copper 63, ejectile here is projectile here is proton, and large number of particles are ejected, so these are all the ejectiles and leads to the formation of the product sodium 24. Now the types of nuclear reaction. Previously we have seen the Bethes notation, and Bethes notation is used for writing the nuclear reaction in the short form. Now the types of nuclear reaction. The nuclear reactions are classified on the basis of the nature of A and B. A means the projectile, B means the ejectile. Always remember this. So based on this, the nature of A and B, following are the types. First one is the elastic scattering. In elastic scattering, A must be equal to B. So projectile must be equal to ejectile, and X is equal to Y. X means target, Y means product. So for example, beryllium 9, when reacts with or bombarded by the neutron, it gives again ejectile as a neutron same, and the product will be the same. So X must be equal to Y, A must be equal to B. Here we can see the description. The incoming particle here in this case is the neutron, strikes the target nucleus, loses the fraction of its kinetic energy in translating the latter. So this neutron, when bombards or strikes the beryllium target, it loses the fraction of its kinetic energy. The projectile particle gets its direction deflected by an angle theta. So when it strikes to the target, it is deflected by an angle of theta, as in scattering of billiard ball. There is no change in total potential energy. There is no change in total, but kinetic energy is conserved. Such process is known as elastic scattering. The amount of energy transferred to the target in setting it in motion translation is given by the relation Em equal to 4m capital M cos square theta upon m plus m bracket square Em, where this Em is initial kinetic energy of the incident particle of mass m, and this Em is the kinetic energy gained by the target nucleus of mass m. This is the initial kinetic energy of the incident particle of mass m. Kinetic energy of the incident particle of mass m, and this is the kinetic energy gained by the target nucleus of mass m. This means that small m is for the incident particle, that is projectile, and this capital M is for the kinetic energy gained by the target. Theta is the angle between the initial and final path of the particle. If E is the residual kinetic energy of the incident particle, the conservation of energy leads to the Em plus Em dash. Em means the kinetic energy of incident particle, and this is the residual kinetic energy of incident particle, and that is the sum of the kinetic energy gained by the target and Em dash. The slowing down of fast neutrons by a moderator in a nuclear reactor is mainly due to the elastic scattering. So this is all about the first type of nuclear reaction, that is elastic scattering. Second type of nuclear reaction is the inelastic scattering. It is a process of scattering considered inelastic if some of the kinetic energy of the particle is used up in raising the potential energy of the target in some way or other, as in exciting it to a higher energy level. If some kinetic energy of the particle is used to increase the potential energy of the target. Here the kinetic energy of the system is not conserved. For example, silver 107, when strikes with neutron, then it gives the silver 107 in excited state, and the ejected particle is now N dash. So here the after absorption or after striking the neutron with the silver undergoes the excitation, and then by isomeric transition it comes to the or it undergoes the excitation, and again we get the silver 107, and the lifetime for this process is about 44.3 seconds. Here the incoming neutron of high energy excites the target nucleus. This incoming neutron excites the target nucleus to an excited state, which in this case has a long life of this second. In this process, the scattered neutron has considerably less kinetic energy. The scattered neutron, this is the scattered neutron, this is the ejectile, and it has considerably less kinetic energy than this projectile. So this is inelastic scattering. In inelastic scattering, after the striking the projectile with the target undergoes the excitation, and after excitation it de-excites after long life of about 44.3 seconds in this case. Third type of nuclear reactions are the photonuclear reactions. Nuclear reactions induced by X-rays or gamma photons of high energy greater than 10 million electron volt are referred to as photonuclear reactions. Here the projectile is gamma and the ejectile is more often neutron or proton, and with some very high energy photons. B may be, means the ejectile may be deuterium, tritium or alpha, or even mixtures of the particles. For example, when beryllium 9 strikes with gamma photons, then the beryllium undergoes excitation, and that excitation is shown as a star with the ejection of neutron. So this is the photonuclear reaction. Photoexcitation, this is also known as photoexcitation. A second example, deuterium when interacts with gamma photons, the neutron with ejection of neutron. When neutron is ejected, neutron has a mass of 1, charge 0. Therefore, after the conservation of charges, it gives the proton. So these are the three types we have studied today. First one is elastic scattering, where A and B are equal and X and Y are equal in elastic. Second is inelastic scattering, and third one is photonuclear reaction.